Shine a laser into cloudy water and slowly tilt the beam. Eventually, instead of passing through the surface, the light bounces completely inward. We are taught that light travels in straight lines. Usually, when it hits a transparent boundary, like water or glass, it easily escapes into the air. If you want to bend that light around a corner, you might think to use a standard mirror. The problem is that standard mirrors absorb a small amount of energy with every single bounce, weakening the beam until it fades entirely. But there is a phenomenon called total internal reflection, or TIR. TIR is an optical effect where light hitting a boundary is completely reflected back into the original material, acting as the ultimate trap with 100% efficiency. Mastering this perfectly lossless bounce lets us bend light around corners, send information across oceans, and power the modern field of optical engineering. To make total internal reflection work, you have to follow a strict rule of physics. The light must travel from an optically denser medium, like water or glass, toward a rarer medium, like air. This animation shows what happens at that boundary. As you widen the angle of the approaching light ray, it hits an exact mathematical tipping point known as the critical angle. This is the precise moment where refraction stops and total reflection begins. Once the angle exceeds that threshold, absolutely zero light is lost to the outside air. By calculating and exploiting that exact angle, engineers turn a block of clear, transparent glass into a flawless mirror. The earliest highly engineered application of this physics trip was the glass prism. Specific materials like crown glass and dense flint glass naturally have a critical angle of less than 45 degrees, making them ideal for precise optical control. Engineers shape prisms so entering light bends at a perfect 90 or even 180 degrees, redirecting images. Due to the rigid geometry, light always hits the interior wall beyond the critical angle, guaranteeing a flawless bounce. Prisms completely solve the problem of image inversion in devices like binoculars, without suffering the severe signal degradation of a standard mirror. But prisms have a physical limitation. They are rigid and fixed. If we need to guide light freely in a complex, twisting direction, a solid block of glass won't work. The solution is the optical fiber, a long, highly flexible strand of pure glass, designed to transmit light over immense distances. Inside, a high-index central core is surrounded by a lower-index cladding. Light bounces continuously off this boundary, trapped by total internal reflection. Since the trap is built into the boundary, the fiber can be bent or tied into a knot without light escaping. This core and climb architecture liberates light from needing to travel in straight lines, thus creating an infinitely flexible optical pipe. Taking this technology out of the lab and into the real world requires bundling hundreds of these microscopic fibers together into massive cables. Everyday audio and video data is converted into laser pulses by devices called transducers. A transducer is a device that converts variations in a physical quantity, like an electrical signal, into another form, like pulses of light. These pulses then travel thousands of miles without losing intensity. You can see the physical scale of this technology when laying the heavy-duty optical cables that form the backbone of the global internet. Engineers also apply this exact same physics in modern medicine, using specialized tools called endoscopes. An endoscope is a flexible medical instrument containing a light pipe that allows doctors to look deep inside the human body. By trapping the light inside these fibers, doctors can safely peer into internal organs like the stomach to make visual examinations without needing to perform invasive surgery. This identical principle even shows up in your living room. Those decorative novelty lamps with the plastic sprays that glow brightly only at their very tips are just bundled optical fibers. By calculating the precise angle needed to trap light inside a denser medium, engineers harnessed a perfectly efficient bounce. That simple physics trick is the invisible backbone of both the modern information age and life-saving medical diagnostics.